Hello everybody, it's nice to see you all again. Today we're going to begin talking about chemical equilibria. Alright, so in this first video we're going to talk basically about three things. First of all, just what is chemical equilibrium. We'll talk about the basis for chemical equilibrium, why it happens. Spoiler alert, it has something to do with kinetics. And we'll talk about the meaning of the equilibrium constant, which has the symbol KEQ. All right, so let's start with this simple example. This is the conversion between cis and trans 2-butene. You may remember from your, when you talked about organic nomenclature, if you have a chain of 4 carbons, and you can see here that this molecule has 4 carbons, right? A 4-carbon chain has the prefix but, and this double bond in the middle, a molecule with a double bond in the middle, gives the suffix -ene, and because this double bond starts at the second carbon in the chain, this molecule is called 2-butene. Okay. Now there are two different ways of making 2-butene. You can have these CH3 groups here on the same side of the double bond or on opposite sides of the double bond. And when those two groups are on the same side, this is called cis 2-butene, and when they're on the opposite sides, then this is called trans 2-butene. Okay. Now that's a little bit of a mouthful. I just wanted to go over that so you would understand what we're talking about when we say cis and trans 2-butene. That's a little bit of, as I said, a bit of a mouthful. So what I'm going to do is I'm just going to call these two molecules cis and trans. And we'll just talk about the reaction, which is the conversion of the cis molecule to the trans molecule. All right, and let's talk a little bit about what's going on with the molecule itself. You may remember from a few sessions ago talking about hybridization and valence bond theory. These carbons here, the ones in the middle anyway, are sp2 hybridized, and they've got that double bond in the middle. So with those being sp2 hybridized, the molecule is actually essentially planar. Like that. And in the middle is this double bond. The double bond has two parts. Remember, part of it is the overlap of these sp2 orbitals, and the overlap of these sp2 orbitals forms a sigma bond in the middle between those two carbons. And that sigma bond has radial symmetry. So if all we had was a sigma bond, it would be very easy for this molecule to rotate around that bond. Since the bond has radial symmetry, it can rotate around without breaking the bond. Okay, But a double bond actually has two parts, and this end-to-end overlap of the sp2 orbitals is just the sigma portion of the bond. There's also a side-to-side overlap of the p orbitals, which forms the pi part of that double bond. Okay? And the pi part of the double bond has two parts above and below the plane of the molecule. And so now, if you try to rotate this, it's very difficult, because in order to rotate it, you'd have to snap or break the pi part of that double bond. Okay? So the pi part of the double bond creates a very high barrier to rotation. It doesn't make it entirely impossible to rotate, but it makes it fairly difficult. Essentially, what we're saying when we say it makes it difficult is that it creates a high activation energy barrier. Oh, before I show you the activation energy barrier, let me mention something else. These CH3 groups here, and here are rather bulky. They're not huge, but they're a little bit bulky. And so when these are both on the same side of the bond, they kind of interfere with each other. They get into each other's space a little bit, and that creates a little bit of stress on the molecule. When the CH3 groups are on opposite sides of that double bond, they don't get into each other's space. There's a lot less stress, and the molecule is a little bit more stable. So that means that the cis molecule is less stable and the trans molecule is more stable. So if we're going to draw an energy level diagram for this, the cis molecule would be slightly higher in energy. Remember, that means less stable. And the trans molecule would be lower in energy. That means more stable. Okay. But if we try to convert from one to the other, we can't just go directly from the cis molecule to the trans molecule, because in order to do that conversion, we have to rotate around that central bond. And when we rotate around that central bond, we're going to break the pi bond. And that creates, as we said before, that creates an activation energy barrier. So the path from cis to trans, the energy path, if you want to say that, looks like that. And that hump right there is the activation energy barrier. This part in the middle is a molecule in the middle of twisting with a broken pi bond. All right, so we can convert from cis to trans, but in order to do so, we have to rotate through, break that pi bond, and overcome this activation energy barrier. Okay, if we heat it up a little bit, put a little bit of energy in there, we can give the molecules enough energy to overcome this barrier, and we will gradually see the cis molecules converting into the trans molecules. Okay? So that's what we want to look at. All right. Now, what we would expect is that if we were to start with a solution that had just trans molecules, let's say at this concentration, and initially the concentration of the cis molecules was 0, right? What we would expect is that because the cis is less stable, gradually concentration of the cis molecules would decrease and concentration of the trans molecules would increase until all of the all of the molecules were converted from cis to trans because the trans is more stable. Turns out that's not what we actually see when we do this. What we actually see this is supposed to pop up, but it's not popping up, so I'm just going to draw this here. What we actually see is the concentration of the cis molecule decreasing, as we would expect, and the concentration of the trans molecule increasing, as we would expect. But the concentration of the cis molecule doesn't decrease all the way to 0. It goes down a bit, and then it kind of plateaus. And the concentration of the trans molecule does the same thing. It increases, and eventually it plateaus. And eventually we get to a point out here where the concentrations of the cis and the trans molecules remain constant. We can let it sit for a long time and they never change. They just maintain those same concentrations. And what we find in this particular case is that this, I didn't really draw it correctly here, but the ratio of the concentration of the trans molecule to the cis molecule is about 1.5. And the interesting thing is we can take this experiment and we can rerun it over and over and over again. We can start with all cis and watch it convert to trans. We could start with all trans molecules and watch them convert to cis molecules. We could double the concentration of the trans molecules. We could double the concentration of the cis molecules. We could make the container larger, make the container smaller. Doesn't matter what we do. Every time we run this experiment, it ultimately plateaus like this, right? In such a way that the ratio of these concentrations is always 1.5. And so this ratio of concentrations is a constant. And we call that constant an equilibrium constant with the symbol K sub EQ. Okay, so let's look at why it is that this reaction always ends up with a constant ratio of concentrations for the cis and the trans, and why it is that the concentration of cis doesn't go to 0. Okay. All right. As you remember from the chapter on kinetics, in general, it's not possible to look at a reaction and immediately know what the rate law for that reaction is. In order to do that, you have to know something about the mechanism. But if you know the mechanism, then you can write a rate law. And for this particular reaction, the mechanism is very simple. Remember, what's happening is we just have the cis molecule converting to the trans molecule, overcoming that activation energy. And in order to do that, the cis molecule just has to rotate that double bond in the middle. There's an activation energy barrier, but it doesn't require collision with another molecule. There are no intermediate species that are being produced. It's just a simple one-step process. And because it's just a simple one-step process, I'm having trouble with my pens today. I apologize for that. Because it's just a simple one-step process, it's a unimolecular reaction. Okay, from the cis molecule going to the trans molecule. So the rate law for this is just going to be really, really simple. The rate is just rate constant times the concentration of that cis molecule. All right. But what's important here, what we're going to be looking at, is both the kinetics of the forward reaction and the reverse reaction. So to distinguish between those, I'm going to put a little subscript F here. So the rate of the forward reaction is the forward rate constant times the concentration of the cis molecule in the solution. And in all cases where there's a forward reaction, it's also possible for there to be a backward reaction. Generally speaking, we've not worried about this, but in principle, this possibility is always there, and we're getting to the point now where this actually is significant and important. I'm going to draw this way in order to highlight the fact that this is a backward reaction, although it's really fundamentally not any different from that, if that's what you wanted to write. All right, so for this backward reaction, again, the mechanism is the same. It's the trans molecule twisting around that central double bond. It's a unimolecular reaction. So again, the rate, and this time I'm going to go ahead and make the distinction right away. The rate for the backward reaction, right, rate sub B is equal to some rate constant, I'll say K sub B for backward reaction, times the concentration of the trans molecule. Okay. All right, so we actually have two reactions to worry about. There's a forward reaction and a backward reaction, both of which are occurring at the same time. And let's see how those two, see what the interplay of those two reactions looks like. All right, so we've got these two reactions going. Remember, the rate of the forward reaction is the forward rate constant times the concentration of the cis isomer. The rate of the backward reaction is the backward rate constant times the concentration of the trans isomer. All right, now I'm going to go back to that color scheme I was using before. remember that if we start with all cis molecules, concentration decreases and then kind of plateaus like that. Meanwhile, for the trans molecules, we're starting in this particular example with a solution that contains all cis molecules and no trans molecules. So the concentration of the trans molecules will gradually increase and then plateau. All right. So let's look at what would happen to the rates here. Okay. So for the reaction rate, for the forward reaction is based on the concentration of the cis molecule. So this reaction rate would start out fairly high because the concentration is high. And then as the concentration of the cis molecule decreases, this rate would decrease. And then eventually, this rate becomes constant. For the trans molecule, the concentration starts out at 0, which means that the rate is also going to start out as 0, since the rate is directly proportional to the concentration of the trans molecule. And as the concentration of the trans increases, this rate is also going to increase. And eventually, we get to a point where the rate of the forward reaction and the rate of the backward reaction are equal. And once we get to that point, the reactions are still happening, but the conversion of cis to trans and the conversion of trans to cis are happening at exactly the same rate. And so the concentration remains constant from that point out. It doesn't mean that there's no longer any reactions happening. The reactions are continuing, but the concentrations are not changing. Okay, so let's see what this kinetic model, let's see how that relates to the equilibrium constant. We said that the equilibrium happens when the rate of the forward reaction is the same as the rate of the backward reaction. And we also said that for this particular reaction, they were simple unimolecular processes, and so it was simple enough to write rate laws for these. Let me add a little note here. Okay. So at equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. That gives us this equation by writing those two rate laws. And then we can just do a little bit of algebra here. And we get this. Okay. So the ratio of the forward rate constant to the backward reaction is the same as the ratio of the concentration of the trans and cis isomer. Now these rate constants are constants. I like to say they're constants, that's why we call them that. That's why we call them rate constants. So if Kf is a constant and Kb is a constant, then the ratio of Kf and Kb is also a constant. So if the left side of this equation is constant, then this means that this must also be constant. Okay. And this ratio of the trans isomer to the cis isomer, which is constant, That's what we define as the sorry for the handwriting. The equilibrium constant. Okay. We'll see a lot of different equilibrium constants for the next few sections. I tend to put KEQ for equilibrium constant. Some people just write capital K. That's fine. If you just see a capital K, understand that to be standing for an equilibrium constant. We'll also, as time goes on, we'll also see Ka, Kb, Kw, KEQ, Kc, Kp. We'll see a lot of different equilibrium constants with different little subscripts down here, but they're all different types of equilibrium constants. And I like to use KEQ as kind of a general symbol for equilibrium constants. All right. Okay, so we'll do another quick example, but before we do that example, I just want to recap all the things that we learned from our first example. Okay. All right. First, all right. So first, at equilibrium, the concentrations of the reactants and products remain constant. Second, even though the concentrations remain constant, the reactions have not stopped. So the reactions are still occurring, just as fast as they ever were. And so we call this a dynamic equilibrium. All right. So the reactions at equilibrium, the reactions are still occurring. However, the rate of the forward reaction is equal to the rate of the backward reaction. And that's what causes the equilibrium concentrations to remain constant. For all right, we have up till this point in the class, we haven't really talked about chemical equilibrium. We've assumed that all reactions go to completion. We make that assumption when we do limiting and excess reagent problems, when we calculate theoretical yields and things like that. And very often that's a reasonable assumption, because for many reactions, the equilibrium is such that the conversion from reactants to products is 99.999% complete. For many reactions, it goes so far toward completion that we can essentially assume that for all intents and purposes, the reaction only goes in one direction. Okay. But in principle, all reactions actually do have some manner of equilibrium taking place, because whenever you have a forward reaction, it's also possible that you can have a backward reaction. All right. When we want to make this explicit, when we really want to focus on the equilibrium, we use a double arrow. So in the past, we would have written this like this, cis to trans. Okay, and actually it's a special kind of an arrow. It's a double arrow, but it's kind of a half arrow. When we want to explicitly consider the equilibrium, you write this way, with this half arrow pointing in both directions. All right. Okay. Let's look at one more example. We can do this one pretty quickly, I think, but I think it's helpful to look at this twice with two different kinds of kinetics. And for this one, maybe you'll be able to work ahead of me a little bit. All right. In this one, let's look at the dimerization of NO2. And NO2 is a simple molecule. I'm going to write this explicitly here, but I'll write it in kind of a shorthand going forward. Okay. So this is NO2. It has a resonance form. This double bond can go back and forth between these two different oxygens, but I won't include that explicitly here. And there's also formal charges on here, which, I'll put them in. A negative formal charge here, and a positive formal charge on that nitrogen. Okay. Now, molecules with odd numbers of electrons tend to be unstable, and so it's advantageous for this orbital with a single electron to overlap and interact with this orbital with a single electron, so that if you get two NO2 molecules together, they're going to react to form, to form a bond in between them. Okay. And put in these electrons. So we've got a negative formal charge here, negative charge here. All right. So I wanted to put all that in there just so that you can see what's going on with this molecule. So you can see that this reaction basically, again, is going to be, in the forward reaction, is just going to be a simple reaction of these two NO2 molecules coming together to form a bond. In this case, of course, it'll be a bimolecular process, all right, but just a collision of two NO2 molecules. And in the case of the backward reaction, it's just going to be the cleavage of that bond in the middle. So that, again, is going to be a simple unimolecular reaction. Okay. Let me rewrite this. How did that happen? Okay, well, I apologize. I accidentally jumped ahead to the next slide. I'm having trouble with this thing. I don't know if it's me or my pen, or I don't know. Doesn't matter. Doesn't matter. So all I was going to do on that last page, I was going to rewrite I was just going to rewrite that reaction this way. Okay, so this is the reaction that we're interested in, and again, our expected results, since the N2O4 is slightly more stable, it doesn't have those odd electrons, we would expect that if we started with a container that contained only NO2, that the NO2 concentration would decrease to 0 essentially, and the NO4 concentration would increase. Now, it takes 2 moles of NO2 to make 1 mole of N2O4, so the N2O4 would only get that high. Okay, that's what we would expect, right? But what we actually see, again, is the concentration of NO2 decreasing, but not quite to 0. Concentration of N2O4 increasing, but not quite double the initial concentration of NO2. And after some point, the concentrations remain constant, and at that point we say that equilibrium is established. Okay. And the we could run this reaction many times using different concentrations, and we will find that there's always going to be a constant ratio here. Okay. Now, there's something a little bit different about this one. Last time, if you remember, when we established equilibrium, what was constant was the ratio of the trans isomer, the product, over the concentration of the cis isomer, which was the reactant. In this case, what's constant is the concentration of N2O4, which is the product, divided by the square of the NO2 concentration. So again, you can run this several different times, different concentrations, different size containers, and it will always be the case that this ratio, concentration of N2O4 divided by the square of the concentration of NO2, is a constant. Okay. All right. So let's take a look at that in a little bit more depth. All right. So if we look at the kinetics here, the rate of the forward reaction, so the conversion of NO2 to N2O4, is going to be some rate constant times the concentration of NO2 squared, because again, that forward reaction is a bimolecular reaction to NO2. Right. And the rate of the reverse reaction, or backward reaction, the texts usually say reverse instead of backward. Sometimes they say backward. I like the B just because the B is a little bit more distinctive. It's easier to see when you're writing these equations here for the rate laws. B stands out better than an R would. All right, so what happens is if we look at the conversion reaction, the NO2 concentration decreases and the N2O4 concentration increases. And so again, what happens is the rate for the forward reaction here, since it's proportional to the concentration of NO2, that rate initially is going to be very high, but will gradually decrease. The rate for the backward reaction, since it depends on the concentration of N2O4, that rate will essentially will will begin initially, is the word I was looking for. Initially, that rate will be 0, and as this concentration increases here, the rate also increases. And so eventually we get to a point where, again, equilibrium is established here. The concentrations remain constant, and at that point, the rate of the forward reaction is equal to the rate of the backward reaction. Okay, so let's look at this one algebraically, just as we did last time. So at equilibrium, the rate of the forward reaction is the same as the rate of the backward reaction. Okay. Because the forward reaction is bimolecular, in this case, the rate for that forward reaction is Kf times NO2 squared, and the rate for the backward reaction is just Kb times the concentration of N2O4. Okay. We can do a little bit of algebra to this, again, just as we did last time. And again, since these are both rate constants, they're constant. And if Kf is constant and Kb is constant, then the ratio of those is also going to be constant. And that means that this ratio of concentrations is also got to be constant, and that will be the equilibrium constant for this reaction. All right, I wanted to do this other example just to show you that sometimes we get exponents in that equilibrium constant expression. We're going to look more at the exponents in a subsequent video. I just wanted to call your attention to that here to show you that those can arise, and they come from these rate laws. Something else that I meant to mention that I don't think I said before. As you recall from the kinetics chapter, the rate constants are temperature dependent. Remember, we had the Arrhenius equation, that fairly complicated exponential function that described the variation in rate constants as a function of temperature. So I keep saying that these are constant, and they are constant, but they're temperature dependent. And so because these are temperature dependent, these constants will change with temperature, and this ratio also changes with temperature. And so the equilibrium constant for any reaction is a constant, but it's a temperature dependent reaction, temperature dependent constant. Okay. All right, one more thing I want to talk about quickly before we wrap this one up, and that is the meaning of this equilibrium constant. We've been talking about it as a ratio, but once you put those concentrations in there, that equilibrium constant actually does give you a number, and I want to talk about the importance of that number. So So the equilibrium constant in general is going to be a ratio of the concentration of the products to the concentrations of the reactants. As I kind of showed you and hinted as we go forward, there will also be some exponents here, or there can be exponents here. We'll look at those a little bit later. But in general, even with the exponents, the equilibrium constant is the ratio of the product concentration to the reactant concentration at equilibrium. In fact, let me put a little subscript here. Okay, because this is true only once you get to the equilibrium concentrations. Okay, so since the equilibrium constant is based on ratios of those concentrations, concentration of a species can never be negative. So both the numerator and denominator must be positive numbers all the time. That means that the equilibrium constant must also be a positive number at all times. Okay? If you ever get a negative equilibrium constant, I can pretty much promise you that you've made a mistake. Okay? So equilibrium constants are always positive. They can be very small positive numbers, like 10 to the minus 6 or 10 to the minus 10. Even things like 10 to the minus 20, 10 to the minus 30 are not uncommon. And they can be very large numbers, like 10 to the plus 6, 10 to the plus 15, 10 to the plus 20, even things like 10 to the plus 30 or 10 to the plus 40. Okay? So equilibrium constants can vary over a very, very wide range. And I want to talk about what that means. So there are basically three different possibilities. First one is that the equilibrium constant is much, much, much bigger than 1. So in that case, we're talking about things like 10 to the 6, 10 to the 20, 10 to the 30, things like that. Very, very, very large numbers. Okay. And when that's the case, when the equilibrium constant is very, very large, what that means is, if you look at this, if you look at the definition here, right? If the equilibrium constant is very large, that means the numerator must be very, very much larger than the denominator. So that means when the solution gets to equilibrium, the mixture is going to contain mostly products. The concentration of the products will be much, much, much larger than the concentration of the reactants. And when that's the case, we say that the equilibrium lies to the right. Or sometimes we also say the equilibrium favors products, right? It's reactions like this that have an equilibrium constant of 10 to the plus 20 or 10 to the plus 30, where we can very easily make the assumption that the reaction goes essentially all the way to completion, and all of the assumptions that we make in limiting and excess reagent problems are valid. Okay. The other, the opposite case, I guess we could say, is when the equilibrium constant is much, much less than 1. Okay, so this is things like 10 to the minus 6 or 10 to the minus 20 or something like that. In a case like that, the concentration of the reactants is going to be much bigger than the concentration of the products. The denominator is much larger than the numerator. That's what gives you a small k. And so in that case, at equilibrium, the reaction mixture contains mostly reactants. Okay, so the reaction really doesn't go very far at all. And in that case, we say the equilibrium lies to the left. And the third case, of course, is if the equilibrium constant is not very large or very small, but somewhere around 1. And when I say around 1, I probably mean maybe 10 to the minus 3 to about 10 to the plus 3. Okay, so not really close to 1, but not extremely large or extremely small. And in those cases, what we would find is that at equilibrium, there's a significant amount of both reactant and product present in the mixture. All right. So if you look at an equilibrium constant, you see the value, you can tell whether that reaction is predicted to go very far to the right to favor products, or if it's going to remain far to the left and favor reactants. All right, fantastic. So good stuff in this one. Equilibrium is super important. So what we talked about is what chemical equilibrium is, and that is that reactions proceed, and as they proceed, they get to a point where the concentrations of the reactants and the products remain constant. The concentrations are no longer changing, but that doesn't mean the reaction has stopped. You have a dynamic equilibrium where reactants are being converted to products and products are being converted to reactants. Okay? And we said that the reason for this, as I just kind of alluded to that, is that this is based on kinetics, and at equilibrium, the rate of the forward reaction and the rate of the backward reaction are equal. Okay. And let me add this. I didn't have this in my slide initially, but I'll just remind you that that equilibrium is going to be temperature dependent because those rate constants are temperature dependent. All right, and finally, we talked about the meaning of the equilibrium constant. If you see a reaction for which equilibrium constant is 1.9 times 10 to the 26, you know that's a reaction for which the equilibrium lies very far to the right, and essentially everything will be converted to products. Okay? If you see one that's negative 26, you know the equilibrium lies to the left, and very, very few of the reactant molecules will be converted to products. At equilibrium, the solution contains almost entirely reactants. All right, fantastic. All right, thanks for sticking with me through that one. I hope that was helpful, and I look forward to seeing you again in the next video.